Yep.
About being late.
Yep.
What if you have something to do that night and you don't understand how to do it, but wait and leave tomorrow?
I have been giving you guys always an extra day. You see what I'm saying? So, the circuit analysis problems that I gave you yesterday should not be due until tonight. All right? Which means you had an opportunity today to come to me at lunch and ask me questions so you could complete it for that night. So if you choose not to use that time, then you chose not to use that time. Which means if you leave it for right at the last moment that night, then you didn't choose your time wisely. And if you then want to still be in fulfillment of the demonstration of learning, you're going to do your best and you're going to turn that thing in. Okay? You see what I mean? So I always give you that extra day so that you can come to me with questions so that you can fulfill the deadlines. That's the way I set the deadlines up. Okay? All right, electrical power. This is another property of an electrical system that we can talk about. We've talked about current, I, that's the flow of charges per unit time, Q over T. We've talked about voltage, which talks about how much energy is being carried by the current, by the coulombs, by the trucks, right? We've talked about resistance, which is a measurement of how many volts are dropped off, or energy, gravel, as the current flows, all right? Electrical power is another property of an electrical system or electrical device that we can calculate. You're probably, well, you know what? Now that we have LED bulbs all over the place, you might not be aware of electrical power as much as, you know, students maybe 15 years ago, not even 15 years ago, 5 years ago, because I could always talk about light bulbs. Does anybody know what the power of a typical, regular, good old-fashioned light bulb, the ones that get really hot, does anybody know what the power of those light bulbs used to be? Any ideas? So you guys don't ever worry about that stuff. In many lamps, it'll say, don't use greater than this type of a light bulb. Any ideas? Does anybody know what the power is for an LED light bulb? Do you know what the power is? No? That's the unit, and that's what I'm going for. It's watts. That's what we measure it in. Does anybody know how many watts an LED bulb usually uses? What do you think, Chloe? 100. Well, 100 is the good old-fashioned light bulbs. A good old-fashioned bright light bulb that got super hot, like you couldn't touch the bulb because you'd burn yourself, was 100 watts, a 100-watt light bulb. But the LED light bulbs don't use as much power because they don't create light by heat. The old light bulbs created light by getting hot. And so they weren't very efficient. They created more heat than they did light. But the LED bulbs don't get as hot. They actually don't get hot at all. The electronics in the base of the LED bulb gets a little hot. Does anybody know what the power is of an LED bulb? This is just a guess. I don't really care. Do you know? They're around 12 and 13 watts. Yeah, they are. 12 and 13 watts. Seriously. So you can see that the power is less. All right? Another thing that students used to know many years ago, back in the day, was if you had a big stereo in your house. Now you guys don't even deal with stereos anymore. You put your little things in your ears and away you go. Take that out, Jess. And you listen to your music in your ears, or you've got a little speaker that you push music out to with a Bluetooth, and it can be pretty loud. But back in the day, and your parents might have one, you'd have this big box with lots of buttons and dials on it, and there'd be wires all over the place to these great big speakers that when you cranked that up, it shook the walls and everything would shake, and it was awesome. And then there'd be like 80s big hair rock and roll, right, to go along with it, and then you did stuff like this, and it was great. But the amount of power that those speakers could push out also measured in watts. And if you had a You know, if you had a 500 watt system with 250 watts per channel, oh man, that was a rocking machine. It was awesome. And again, you guys have no idea how much power necessarily comes out of your devices. So it becomes a little tricky to talk about electrical power because you guys don't have the same examples that we had when we were dealing with big old stereos and light bulbs that got super hot. But let's see if we can get some information across from it. So what is electrical power? All right. Electrical power is the rate in which electrical energy is produced or is used. All right. So we're talking about the energy. So we're talking about the energy that is either produced by a source. So a battery would have a certain amount of power. It could send energy out only so fast. So it's like a speed. A generator would have power. All right? You going to take these notes, Jamie? A generator would have power. Okay? How many people have a generator at their house? What does it say on the side for the amount of power it can produce? Nobody looks at it? No? Any ideas? Volts is voltage. We know volts. That's not power. That's how much it can produce. How many watts? 120 watts would be a very tiny generator. Oh, so if it's 120 watts, then maybe it's 120 watts. If you've got a big generator with a big engine on it, it may say 6,000 watts. All right? Or it may say 3,000 watts. Okay? All right? So generators have a power, how fast it can produce electrical energy. Loads use electrical energy. Light bulbs, they will use 100 watts. That's how quickly it's using the energy. All right? Speakers, lots of energy that it can use when we're cranking it up. But any electrical device, I turn on this fan, it has a certain power. It will use the energy at a certain speed. I can change the power output by changing the setting on the fan. Oh, it's fun. It's plugged in. I didn't think it was plugged in. I can make the fan go fast and therefore consume more power. All right? It's using energy faster. I can turn the fan down, if I know how to do it. I can turn the fan down and it's now using less power. It's using less energy faster. So it's how quickly it uses energy. All right. There's the equation. Excellent. Kyla is looking over at the equation saying, wait a minute, something looks really familiar about that. Excellent. What do you notice, Kyla, that's similar about this equation to the one that you were just looking at? Time. Excellent. Time is on the bottom. This is the speed at which energy is used. Time on the bottom. All right? It's going to be in seconds. Good job. Current is the speed at which the charges flow. It's a different speed. That's how quickly the charges are moving. This is the speed in which the energy is being used. We've seen E. Yep. Joules. James Prescott Joule. Capital J. P. Power. It's in technically joules per second, but we pay homage again to a scientist who works on stuff about power. It's watts. Again, a scientist's name, so it gets a capital W, because if it's named after someone, it's a capital. We're going to do a question with it or two and when we get going. Again, just as practice, but I'm not going to give this to you. Boy, that's a big triangle, isn't it? A little overkill. What goes in the top of this? Parker, what am I going to put in the top based on this equation? E. E, P, T. I'm not even going to write down the others anymore. I hope we can use it. Okay? Now notice, and again, Kyla looked right over at our other equations, which is awesome. Yes, T is in common with that, but you'll notice that E is in common with what of our other equations? E is in common with which of our other equations? Yeah, Rachel? The voltage one. Wow, you are smarter on the other side of the room. Good job. The voltage one. If this was a higher level of physics, I'd have you put together a group of equations to make a new equation. I'm not going to make you do it. I'm just going to tell you the other version. Because there's T in common with the I, and because there's E in common with the V, if we do some math, we can create a different version of the power equation in terms of I and V. So there's two ways in which we could calculate power. If we want to know the energy that's being used, I need to know the time and the power. If I know the current and the voltage, I can still get the power because it's a combination of those two equations put together. We'd do some nice algebra, we'd cancel some stuff. It's awesome. It's fun stuff. You'd love it. But I'm going to spare you that. I could actually make you go back to the circuit analysis sheet, and we could add one more thing to each of those three. Because if we know R, and we know I, and we know V, what else could I calculate if I know I and V? Yeah, what could I get, Jade? I know we can get R, VI and R. What else could I calculate now? Yep, I could calculate the power. We could also calculate how quickly the battery would produce energy or the loads would consume their energy. Another property of an electric device, whether it's a motor or a power supply. Yep. Things in an equation, like an equation that has 4 or 5, not what we're doing in this course, but in real physics, there's all kinds of them. Yeah. If you were to continue on and you were to take physics with Mr. Petrus, you would learn what's called the universal law of gravitation, and the force of gravity would be equal to capital G times M1 times M2 over R squared. Yeah, that's good stuff. That's the force of gravity that's felt between any two objects of mass separated by a distance of r, and that's what we use to calculate, like the moon's, orbit. We can calculate all kinds of stuff with this. For us, it'll only be 3. Yep.
Did you say you just take those two and multiply the top 16?
Oh, look at you interested people. Let's say that this is the Earth. We could call that M1. And let's say that this is the moon, we could call that M2. We would know the mass, we would need to know the masses of them. And if I know the distance between their centers, which we would call the radius of its orbit, I could put all that information in that equation and get the force of gravity. G is a constant. It's a special number. We're not doing that math. Let's go back to this. Only 3. What's this one going to look like? Yep, what do you got?
I don't have the answer.
Oh!
That is the best circle. So fast.
It's so good.
Yeah,
That was truly.
that's part of my teacher training, making good circles on the board. No, let's keep going here. Let's keep going here. Don't be distracted by my perfect circle. Because if I have to do it again, it'll end up being Charlie Brown's head, right? If it fails, then that just looks bad. Somebody, let's keep focusing here. Are you going to tell me something here? Yes, please do. The P goes on top, IV. Because when it's a fraction, the top of the fraction goes there. But because the bottom is a multiplier, because these multiply, the multipliers go on the bottom, because they got to be multiplied. Let's do some calculations. Oh, don't be groaning. Okay, let's write this down. You can figure that out for yourself.
No, I did it wrong, didn't I?
This is a P.
Oh,
That's all right. A TV is connected to a 120 volt outlet. That, by the way, is the standard voltage of a plug. And when it is running, it is drawing 1.5 amps of current. Well, if this was yesterday, if we knew V and we knew I, what would we calculate? If this was yesterday, we'd find R, because we'd build its triangle and away we go. But now, when we have V and I, we can also get P. It's a different version of the equation, but we can get it. So, we have two equations for P. One is energy and time. The other one is current and volts, amps and volts. Given my information, what equation am I using to calculate the power of the TV based on the information I'm given above? Which version of the equation am I using? Yep. You're telling me the calculation, that's awesome. What's the equation I'm using, Danton? P equals IV. I just want to write down the steps, but you're right. This is for A. Determine the power of the TV, because I'm given the V and I'm given the I. Well, we're not there yet. We don't have any information for it yet. We're not ready for it. Again, if you're unsure, write your information down. V equals 120 volts. All right? Again, I don't have to see that, but you know, if you're not sure what to do, you got to write it down. A is amps, 1.5 amps. So I need the power equation that contains the amps and the volts. So 1.5 amps times 120 volts. What is the power of that device? Yep, what do you got? 180. What is the unit? Watts. Excellent. 180 watts is that particular device. Okay? B. If it was left on for 2.5 hours, how much energy did it use? Now, I know the P from the previous question. I've just calculated it. What does 2.5 hours tell me? Which variable is 2.5 hours in our equations thing? Yep, it's a T. T equals 2.5 hours. I know the P from above, 180 watts. What can I find? Jess? E. E is equal to, sorry, what's it going to be? P times T. We've got one problem though. What does the T have to be in? It's got to be in seconds. So, let's first change the hours into what? Well, to go directly to seconds, we need to do a big calculation. So let's do it as steps. What do I have to multiply to turn the hours into minutes? 60 times 60 minutes, because there's 60 minutes in each hour. Now we're to minutes. How am I going to turn the minutes into seconds? Yep. Times 60. Times 60. All right? And I didn't leave nearly enough room, so I'm going to have to put that down here. Equals. T equals. How many seconds will that be? Yep, Marshall? 9,000, exactly. 9,000 seconds. Okay? Now we're ready to go. The energy is equal to the power, 180 watts, times the time in which it's running, 9,000 seconds, and how much energy was consumed by the television as it ran for that long. Rachel, got an answer? You're just stretching, just yawning and fixing your hair? Do you have your calculator out? Well, why don't you push some buttons and, get that calculator to run? See if you can get some numbers. We seem to be depending on the regulars. Robert, how's that calculator working for you? Oh, would you like to borrow one? Come on up and grab one on the front of my desk here. Robert, have you started a new binder? Because if you're looking, your old binder's over there. Along with your textbook. Oh. I've been wanting to do that for days, but I keep forgetting. Okay. Do you have an answer, Rachel? Oh, you're disappointing me completely. Jay, tell me the answer. Just tell me the answer, Jay.
I don't know how to say it.
Just tell me the numbers, the digits. 1, 6, 2, 1, 6, 2, 0, 0, 0. 1, 6, 2. Now how many zeros? 1, 2, 3, 4. That's okay. That's all right. What's the unit? What's the unit for energy? Joules. Joules of energy. All right? And if you want to know how to say that, that looks like 1,620,000 joules, but that's okay. All right? You could put it in scientific notation if you want to do that. That would be cool too. Okay. All right. Another question.
But there's only one number in that.
There is. You're right.
Oh,
Read it through. Read the question. Write it down, and as you write it down, you'll read it, and hopefully you'll...
I know. Did you tell us?
I just told you moments ago. Everything I do is for a purpose, Jessica.
I was writing to my mom how good of a teacher you are.
Now you're just trying to butter me up.
Because-
This is a pre-test butter up here is what this is, right?
No, actually, I was, because I didn't understand it. You explained it like dump trucks, and I understood it.
Dump trucks. I like dump trucks. Are you going to tell me something, Marshall, or are you going to comment on my awesome circle?
Let's just say Steve forgot what the standard outlet.
Ah. That's something that I'd like you to know, because that's just good information. Yeah. Let's say that came across a test and you were really, really desperate, and let's say I expected that for you to know it. Let's say the question was out of 4, and I told this person that number. I would likely take with a little red pen a -1, and now your final one could only be out of 3. You see what I mean?
Let's say that this person has almost short-term memory loss.
Let's not worry. Let's not worry about that right now. We'll deal with that later on. Did I? Oh, that's my pet peeve, spelling mistake. Okay. Come on, folks. Let's keep going. Let's keep going. This is pre-spell check. I'm serious. That's how old this is. The little red line didn't underline. Yeah, by all means. There's always one on my desk. Just come on up and grab one if you need one, okay? Come on, folks. Let's get this finished so you guys can get to work. So, 100 watts. What variable is that? P. The information that is hidden is the voltage of a standard outlet. Jess? 120 volts. Now, if you were to take a voltmeter and jam it into a outlet, you could do that. You could do that. I'll show you in a moment when I'm done recording. It may not read exactly 120. It can fluctuate depending on the electrical surroundings, whether there's a lot of electricity being used in another part of the circuit, could be another part of the building. That can go up and down. I've seen it as low as 108, and I've seen it as high as 125, 126. So it can fluctuate, but it's right around 120. What am I trying to find in this question? What am I looking for here? Rachel? So which symbol is it in the equation? I. And what's my equation after rearrangement? What's my equation? Using the handy-dandy triangle or doing some math. Did you find it, Jenna? What is it? P over V. 100 over 120. What's the current through that circle? Tristan?
1.2.
That would be upside down because the littler number's on the top. So don't use a calculator. Jay, what do you got? Unit? Unit. The current unit, correct. Coulombs? Nope, that's a charge unit. Amps. Okay. All right. So, the final thing I want to talk about before I let you do some work is electrical safety. What the heck? 8.3 amps.
Thank you.
The final thing I want to talk about before you guys get to doing some work is electrical safety. All right. As I stated, if you were to take a voltmeter, right, and you were to jam it into an outlet, now this is AC current, because our electrical systems run on AC, and I'm going to turn this to 400 volts max, and I'm going to put that right here in front of my coffee cup, and I'm going to unplug that. And I am going to put this in here. Trust me, I know what I'm doing. All right, here we go. What's it reading?
127.
What's it reading now? 125 volts. Now you'll notice that the machine didn't cause the whole system to beat, right? Why does it keep changing? Because different people are plugging in different things. Electricity is being drawn to another part of the circuit. That causes a little bit of a voltage drain. Have you ever noticed in your houses before, sometimes for no apparent reason, the lights go dim a little bit and then they come back up? Something has happened in the massive electrical circuit that exists in Ontario, all right? There are power sources feeding electricity into it, things like turbines and nuclear generators and waterfalls at Niagara Falls. And there are things pulling electricity out of it, like my projector or the computer or anything we plug into it. So it will fluctuate. Now, if I were to take this pair of tweezers and jam it into the outlet, don't do that. Don't do it. My brother did this when he was a kid. It was awesome. As soon as he put it in there, number one, the heat generated in the socket blew it across the room, and then I think it stuck in the drywall. It was awesome. And then the lights went out. Now, why did the lights go out? Yep. The circuit was shorted, but why then did the lights go out? Yep. You tripped the breaker. So in our circuits, in our homes, in our buildings here, I'm not supposed to have access to this, but anyway, in our buildings, you have what is called a circuit breaker, and there are circuit breakers in there that protect us, all right? So circuit breakers, and then there's another device that can protect us. What if it's your car? Have you ever noticed maybe a certain feature in your car doesn't work all the time that it should work? Like my seat warmer. The seat warmers are the greatest invention ever in cars. And on my previous car, my seat warmer didn't work anymore, and I was sad. Yeah. Does anybody know why the seat warmer probably stopped working? Any ideas? Yeah? Something happened in the circuit. You're correct. Either the heater itself was broke, or there's this device that exists in cars and many electronic devices that prevents a short and something happens to it. What am I talking about? A fuse. Have you ever heard of a fuse? Okay. A fuse is a special little device that has a little piece of metal in it that if too much electricity flows, it melts the metal and it breaks the circuit. Both of these devices protect us. Did you guys get the title, Electrical Safety? They protect us from a dangerous situation in a circuit. Okay? Yep.
Okay, so I can't quite remember what they're called, but so you plug them into an outlet and they have like multiple other little outlets like plug-ins.
Yes, correct. So you could have a power bar or perhaps some kind of expander.
Like, does it add more, I guess, like energy into it? So like you can have like it plugged into it, it's like more, so it's like it has to use more. But
It's gonna draw more this. The voltage will be the same. They'll all plug into 100, but everything that plugs in has a power. And if it has power, and they all do, it's gonna draw what? What is the word we're gonna use? It's drawing this. It's drawing power. Current. It's drawing current. So if you plug in on a power bar your charger for your phone, right? And your hair dryer, because you're in your room and you're going to dry your hair. And it's the winter, so you also plug in your little space heater that your parents got you for your room because it's cold, because I live in an old farmhouse, so there's a space heater in there. If you keep plugging in things, what eventually happens? Yep. Trips out. Some power bars have their own circuit breaker in the power bar, and then the power bar just trips out. So every time you plug in more current flows in to those machines, and eventually the circuit is overwhelmed. Current in a circuit makes things hot. Toasters draw lots of current. Hair dryers draw lots of current. And it's because they have a high power. Okay? The power makes the electricity flow fast, and it makes things hot. If you don't have a circuit breaker, and you have all these things making the wire get hotter and hotter and hotter in the wall, what eventually happens? If the wire just keeps getting hotter, and nothing stops it from getting hotter and hotter, what's going to eventually happen to that wire in the wall? Well, it'll melt the coating. Then what? Start a fire. That's not good. We can't have fires in homes. That's not good. Okay? So the circuit breaker protects it. Yeah.
so okay. I have like the thing that's backing up and then breaking. I have one of those like anyways,
So you have one of which? You have a circuit box in your room? Wow, that's awesome.
yeah, anyways, so how come if like a outlet trips out, then how are you supposed to like make it so it's not tripped out again? Because like I know that like there's a bunch of switches on it, but if
Okay. Each circuit will have a switch. So like a room, like a living room, or the kitchen, or the outlets that service the kitchen back there where you plug in your coffee maker and all those high, each one will have its own breaker. If it keeps tripping, you're plugging too many things in. Don't plug so much in. It's that simple. Or connect it to a secondary circuit so it's running off of two breakers. All right? Sometimes a breaker can trip if it gets old and faulty, and then it may need replacing. Call an electrician, right? Because all of that stuff back there is live electricity, right? You touch a cross there with a couple of screwdrivers and it doesn't end well for you, okay? All right? So if it keeps tripping, don't plug in as much. All right. If a wire or electrical circuit carries too much current, it will get hot. This can melt the plastic coating and cause a short in the circuit, and this can be a fire hazard. All of these different things, circuit breakers, if you've ever seen the circuit breaker, you'll notice there's a little number on the end of it. I can't see, I don't know if my glasses on. What's it say on that switch? 15, 10? 15. So that means 15 amps of current can run through this device before it trips, okay? Before it trips. Fuses, and this is an old fuse, and we actually rented a house years ago when me and my wife first got married. Some old houses had these old fuse panels, and you'd put these fuses in there. They almost look like light bulbs on the bottom. You screw them in. If the electricity went too fast, it melted the wire, broke the circuit, done. The problem with a fuse is that once it's done, what do you do with this? Yeah. You throw it in the garbage, you get another one. You can't put the wire back together. The nice thing about a circuit breaker, what happens when you trip it? Yeah, you just trip it back, you reset it, and you're good to go. These are about $50 a piece. These, I used to be able to get like a whole box of them for like $4, right? But you throw these out, and these you just keep resetting. Let's write a little bit down about the difference between fuses and circuit breakers. Oh, actually, I don't need Bunsen. We'll do it Bunsen. In a circuit breaker, there is something called a bimetallic strip. What an awesome 2 words to put together. Bimetallic. That's a transparent cover to a circuit breaker. Most of them don't have a transparent cover. This is for teaching purposes. But there's a whole bunch of stuff in there that you can't see anyway. I've taken one apart, and on the inside, there is a lever, right, that has this pivot piece that then connects to this piece here, the middle metal piece. That's the bimetallic strip. When it's up in this position, it's connected. The circuit runs and the electricity flows through the bimetallic strip. When it gets hot, a bimetallic strip bends. This is a bimetallic strip. This is a demonstration bimetallic strip. How many metals do you, oh, this is still connected to 120, isn't it? How many metals do you think there are in a bimetallic strip? Yep. It's bimetallic, like a bicycle. 2. There's 2 metals, 1 on each side. When they get hot, they expand, but one expands faster than the other. I'm not going to use electricity to make this bend. I'm going to use the Bunsen burner's heat. If I can find my lighter. Oh, there it is. Got to get the gas going. Okay. That's for cold. If I take the bimetallic strip and I heat it up, you see what it did? It bent. If I cool it back down, see it nice and straight? So the one on my left, your right, expands faster than the one on the other side. And when it gets hot, it bends. And when it gets cool, it straightens out. Okay? That's what a bimetallic strip does. Right? That tells me it's hot. I could use this as a thermometer. I could actually have it bend on a scale, and it would tell me how hot something is. When you have too much electricity flowing through the circuit, this little bit of metal bends and trip. It opens the circuit. No more electricity. Have you ever ran downstairs? Well, it used to be in the basement at my parents' house. My mom would be vacuuming. There'd be something on. It would trip the breaker, and she would say, "Hurry up, go trip that breaker back." Have you ever gone very quickly to the circuit board and tried to trip the breaker back? Does it always go back? No, it doesn't go back. Why is it not going back? Why is the breaker not resetting, and why do you have to wait for a while to reset it? What do you think?
Still hot.
It's still hot. The bimetallic strip is still bent, and it's saying still not safe to run electricity. Things are too hot still. Wait for a moment, the bimetallic strip resets, and you're able to use the electricity. Okay. This is my last question. This is the last question of the day. What are you talking about? Oh, yeah, you have to get the information for the question in order to answer it. But it won't be here. But as long as you know how to calculate it, that's your call. A 1200 watt hair dryer and a 1750 watt curling iron are connected to a circuit protected by a 15 amp breaker. Will the breaker trip? Well, and it's connected to a standard home circuit. All right? Yep. There's two ways in which we can do this problem. You can add power together and do one calculation, or you could do two calculations for each of the powers and then add your final answer together. I like to do them separately. I want you to do it by adding the powers together. I want you to do it differently than I do it up here. Okay? Now, here's how we do this. I'm not going to use the 15 amps. I'm actually going to calculate amps because I want to know whether the amps exceeds the circuit breaker. So I'm actually solving for amps. In this case, I have to find I. All right? What's the voltage going to be if this is connected to a home circuit? This is connected to a home circuit where you would use your curling iron. Marshall, where would you use your curling iron? You'd use it. I don't think you've ever used a curling iron in your life. What's the voltage going to be of that home circuit? Oh, no, I don't have time for that. I want to get this calculation done first. Go.
Okay, one time I took my sister's curling, eyelash curler, I thought it cut out my eyelashes.
Okay.
And then curled it really weird.
Oh, that's exciting. That would be a good look for you. Now, Marshall, you got to tell me how many volts is in a home circuit. 120. I. What's my equation for getting the current? Yep. What's my equation for getting the current? Find your triangle. Is it P over V? Yeah. Is it? P over V. For the hair dryer, how much current is it going to draw? 120 watts over, 1200 watts over 120 volts. How much current does it draw? Yep. Too many zeros. Should be 10. Should be 10. 10 what? What is the unit for current? Amps. The curler. How much current will it draw? How much does it draw? Yep, Rachel? There's got to be a decimal in there somewhere. 14 decimal. Okay, so let's go with 5/8. That's good enough. Amps. Okay? Is the breaker going to trip? Yes, you can. Yes, you can. I'm going to explain that in a moment. Will the breaker trip? Yes, because the total current, I total, will be 10 amps plus 14.58 amps, which is equal to what? 24.58 amps. We're tripping this like crazy. It's only rated for 15 amps. 24 amps has flown. So, yes. Oh, I know. So, the question was, can you add powers that are on the same circuit? The answer is yes, you can. Two ways to do this. We could have done this once, except with an addition of the two powers calculated as one. All right? And that would work. Yes.
So on the test,
I don't care which way. I don't care how you do it. I just want you to get the right answer and to show me how you did it so it makes good logical sense. Yes.
why wouldn't, when you do it separately like that, why wouldn't it be like for, like I equals, 1,200 over 60 volts? Because it's half of it.
No, it's not half of it. In a house circuit, all outlets are 120 volts because they're all connected in parallel. Because each device has been designed and created for 120 volts. Everything that you purchase in Canada that plugs in with a plug is designed for 120 volts. If it were to be plugged into 60 volts, it would not function. It's not designed for that. Now, I was going to talk a little bit about electric shock, and there's a little video there, but I want you guys to get to work, so I'm not going to talk about this right now. There's a worksheet. I'm not collecting this worksheet in, but I want a picture of it as a homework check, right? Do it. Take a picture of your work, homework check. It can be done on paper. It doesn't have to be done on the worksheet, but I want you to take a picture of your work and submit it just as a homework check. Let me stop my recording so I'm not talking to everybody online here or on whatever. Stylus is right there.